Hey everybody, welcome back. So last time we introduced the idea of acceleration, which was a change in velocity. Well, there's a special case of acceleration that is really often very useful, and that's when we have a constant acceleration. Now, kinematics is simply the description of motion. It's figuring out the equations that describe how this thing is moving. Not talking about why, or not talking about what's causing it. We're just saying this is what it's doing. However, when most people talk about the kinematics equations, they are usually referring to the special case of constant acceleration. So what we're going to do in this lecture is we're actually going to derive all three of these equations of kinematics, these kinematics equations. And if you had any physics in high school, you may have seen these before. These may look fairly familiar to you, but at the time you were told just memorize them. And you didn't know why they were what they were, in particular why these particular constants were in front of the different terms. Well, the reason for that is in order to actually derive them, you need calculus. So since it's a calculus-based class, that's what we're going to do. And it all starts from the concept of acceleration and our definition of acceleration. Now, once we've derived each of these equations, I want you to make a flipbook page for each one of these. And I'll kind of give you some ideas of what that flipbook page should look like. But the idea with the flipbook is we don't memorize anything, ever. Because even if you're 100% sure that it's right, well, you look it up anyway. Because if for some reason you're wrong, well, somebody might just die. On the other hand, you don't want to have a lot of text here, because that makes it hard for you to find what you're looking for. So we've got to find that balance, and I'm going to give you some ideas of how to do that. And from here on out, you're going to want to make a flipbook page for every single new tool or equation or whatever that we derive in this class. That way you've got everything in your little book. When it comes time to do the exam, you'll have everything that you need right away. All right, let's get started. All right, so open your books to the kinematics constant acceleration section. And as I mentioned, what we're going to start off with here is all of it is going to start from the definition of acceleration. And that's what we've given right here. So let's take a look at that, and let's start with that. So we're going to say that a, which is a vector, is going to be the derivative of the velocity with respect to time. All right, so the first equation that we want to come up with is a velocity versus time equation. So these are going to be the names that we're going to give to each one of these equations. So to find the velocity versus time, I've got the acceleration. What's happening with the velocity right now? Well, the acceleration is the derivative of the velocity, so I need to do the opposite of that. So looking at microtask 1, what is the opposite of the derivative? That's going to be the integral. So we just need to take the integral of both sides. So let's do that. All right. So now we want to see how can I get to just getting the v, because as you see here, I can't integrate something that doesn't have a dt on it, or some sort of differential on it. And also I'm not going to be able to integrate this with two differentials. So let's move to the next slide then. Now we're going to start with our equation. We're going to do it right here where you can see it. So we're going to start with a is equal to dv dt, like that. Let's multiply both sides of the equation by dt. And so I get both of these are vectors, dt is equal to simply dv. All right, simple as that. Now this may give your math teacher hissy fits because there's no less the derivative of v with respect to time, but it's also a fraction. And so it behaves like any fraction. So I'm simply multiplying both sides by dt. I get a dt here, and then it cancels the dt down here and leaves that. All right, so the next thing we want to do, step 2, is then we're going to integrate both sides of the equation. All right, so that's going to give me the integral of a dt, a is a vector, is equal to the integral of dv. Now, here's where our assumption comes in. We are assuming that a is constant. If a is a function of time, I can't pull that a outside the integral sign. I have to do the integration with it there, and we've done similar things to that before in previous lessons. So with the rocket powered robot, for example, where I don't have a constant acceleration, this a is not a constant, and so it can't come out. We are assuming a constant acceleration, and in your flipbook, that needs to be one of the first things that you have, is all of your assumptions, because if that assumption doesn't hold, you can't use this equation. It will not work. And many times I find students on an exam who are trying to solve something and then go, oh, I like the kinematics equations, I'm just going to use those. And it wasn't a constant acceleration. And so in this case, there was no way you could use the kinematics equations. You had to start from scratch doing this integral. For us, though, for this equation, we are assuming it's constant. So that means I can pull it outside. So I get a integral dt equals integral dv. Now, the integral of a differential is simply whatever quantity that I'm doing here. So the integral of dt is simply t, and the integral of dv is v. I'm going to put it up here so I've got a little bit of room. Integral dt equals integral dv. All right, so that means that I have something like this, and I'm going to integrate from ti to tf. Oops. And then I'm going to integrate v from vi to vf. Okay? Now, your calculus teacher may have just drawn a straight line here or whatever. I like to put it in brackets so that I know exactly what it is that I'm going to be plugging in this tf and ti for. All right, so as you know, when I take the integral and I plug in my limits here, it's simply going to be a times tf minus ti is equal to vf minus vi. And if you want to put that in parentheses, you can, but there's nothing else there, so it doesn't matter. Now here's the second assumption that we're going to make. We have the freedom to start our clock anytime we want. So why not start your clock at the time that you're interested in seeing this change in motion? Because remember, kinematics is a description of the motion. If we start our clock at that point, well then our initial time is simply going to be 0. Now the final time then simply becomes the elapsed time from wherever I was interested in the motion. So I could have this robot moving, but if I'm only interested in from here to here, then I only need the elapsed time between these two. I don't care what's happening back here. So to represent elapsed time, we're going to use a simple t with no subscript. So that brings this down to how at equals vf, these should be vectors, minus vi. Okay, well we want that our velocity versus time equation. So I want to know, after a given time, what is going to be the velocity? So we're going to solve this equation down here, number 3. We're going to solve that for vf. So let's copy it down here. We've got a times the elapsed time equals vf minus vi. And remember, that's the elapsed time. It might not be the total time. And what we're going to see in just a minute is we're going to have to break down our problems often into phases whenever the motion changes. And so the elapsed time is only going to be from this part to this part, or this part to this part. All right, solving this for vf is pretty straightforward. So I just need to move my vi to the other side. So I get vf is equal to vi. It's positive because I moved it over here, plus at. Now, if that gives you the heebie-jeebies and you're like, well, no, I need to move my vi over here, so I've got vi plus at equals vf, that's okay. But you are going to see me often, I want to have that term that I'm trying to get out of it. I'm often going to want to have that on the left-hand side, but honestly, it's the same thing, so you can do whatever you want. So let's check our units. Each one of these units must have units of velocity because vf is a velocity. So this one should be meters per second. Well, it's just the velocity, so of course it is. This one, this vi, should also be meters per second. And again, that's a velocity, so that's not a problem. Now let's look at this one. What are the units of acceleration? That's going to be meters per second squared. And then I'm going to multiply by seconds, which are the units of time. One of those is going to cancel, and I'm going to be left with meters per second. So this term is a velocity. Think about that. That term is not just at. It physically represents a velocity. And if we try to interpret this equation physically, then what I'm saying in words is the final velocity is equal to whatever velocity I had to start with. That makes sense, right? Plus whatever velocity I got as a result of my acceleration. Well, I don't want to have to do a whole new thing for that every time. So let me just erase it there. Instead, we know that the velocity as a result of that acceleration is the acceleration times however long that acceleration has been running. The longer that acceleration runs, the more velocity that's going to give me. If I don't have any acceleration at all, well, then that's going to be 0. And my final velocity is just always going to be my initial velocity from that. By the same token, if I have no initial velocity, let's say I start from rest, then all of the velocity I get comes from that acceleration. And the longer that acceleration runs, the faster my final velocity is going to be. All right. Okay, so it works, and it does a pretty good job with that. Okay, so now that we have our first equation, I'm going to give you a sample here of what your flipbook should be looking like. Now remember, the point of the flipbook is to allow you to access the information you need quickly. As an engineer, you never memorize anything. If there's an equation you want to know, even if you are 100% sure you remember what it is, you reach up, you pull out the equation, you look it up, and you write it down from there, because if you make a mistake, somebody's going to die. So, but you don't want to have to go thumbing through a textbook for this. And from a practical standpoint, when you're taking the exam, you're not going to have a lot of time to do that. So you need to get your flipbook in such a way that you can access the information you need quickly. So let's take an example for this with our velocity versus time equation. So your flipbook should be the spiral bound 3x5 index cards. That's by far the best way to do it. So the first thing you want to do is you want to have the name of the tool or the equation. So in this case, that is the velocity versus time equation. All right. Then the very next thing, you want to list the assumptions that you're making, because if the problem you're looking at doesn't satisfy these assumptions, don't use this problem. So for example, in the exam, if you have a time-varying acceleration, like the rocket robot, you cannot use the kinematics equations that we've derived, because our first assumption is assumes constant acceleration. If that is not true, do not even go there. Don't use this equation at all. It will give you the wrong answer. You're going to have to go back to the full method where you're taking the derivative or the integral, depending on which one you want, and figuring out from that what the information that you need and coming up with a whole new unique equation. You cannot use these shortcut equations for this. They only apply for a constant acceleration. Okay, the other assumption that we made, we assume that the initial time was 0. That way the t becomes our elapsed time. So if for some reason your initial time is not 0, okay, again, you need to go back to the equation and you need to modify it to take that into account. You basically need to start over with it. Right? So if these two things are true, then now you can use the equation. So the next thing we want to put on here then is the equation itself. And so that's VF equals VI plus A, which is also a vector, T. And then you need to list what each of these symbols means and what their units are. Remember, you can use any symbols you want. You can call it smiley face if you want. It doesn't matter as long as you define it. So here I'm saying VF is the final velocity in meters per second. VI is the initial velocity in meters per second. A is the acceleration, and if you want to remind yourself that it's a constant acceleration, that's fine. So this is the acceleration in meters per second squared. And then finally, this is important, T is the elapsed time. And I misspelled elapsed there. Let's try that again. Is the elapsed time in seconds. And that's your flipbook page. And it should look more or less just like that. I mean, you have the freedom to set this up however you want, but I've been doing this a long time, and I can tell you I still do it this way. So I think you will find that this is a method that will work for you really well. I still have my flipbooks from college. I've copied them over maybe a few times because they were getting faded, but I still use them, and I have used them throughout my career with this, so you will too. Okay, so let's take a look at the second equation that we want to derive from that. And I'm going to erase all this, which is going to take me a little bit of time. But what we want to do now is we want to find a position versus time equation. So we know we've got an equation for the velocity versus time, and we're going to use that. But now we want to see what if we don't know the velocity, the final velocity? Maybe we want to know the position. Okay, so we're going to start right here. We're going to start with our velocity definition. So our velocity is the derivative of x with respect to time. And remember, that's a vector, and so x becomes effectively the displacement. Okay, so in order to do this, then I'm going to take that velocity versus time equation that we just derived. So I'm going to write it here for our reference. So VF equals VI plus AT. That's the velocity versus time equation. We're going to take this. This is going to be our final velocity. We're going to plug in for VF here. And so that gives me VI plus AT is equal to dx over dt. Okay. And that's what you see right down here. Now, you'll notice that I have these subscripts x. So I've got like Vxi and Ax here. Right now, we're working in one dimension. And as you know, that one dimension, that x dimension that we're working with can be this way, it can be up, it can be at some angle. You have total freedom in how you want to set the orientation of that. Eventually, though, we are going to be working in two dimensions at the same time. So you'll have two coordinates to specify. Well, that doesn't complicate things at all, because all we do is we look at each coordinate separately. So I might have, maybe I called this one time, or let's see, maybe I called this one x and I call this one y, or whatever you want to do. I would look at the x kinematic equation and the y kinematic equation, and I just treat them separately. Since we're only working in one dimension here, technically it's going to be the x component, but the velocity is a vector, and so we wanted you to keep that in mind for later on. All right, so let's look at the next slide. So on the next page in your book, then, we're going to take that equation and we're going to multiply both sides by dt, because remember, when I had vi plus at is equal to dx dt, I cannot integrate that. I want x, I want the position versus time. But remember, I can't integrate because there's no differential on the left-hand side, and I've got this fraction on the right-hand side. So I'm going to multiply both sides by dt. And let's do that over here so that we can see that. So that's going to give me vi dt plus at dt is equal to dx. And that's a vector. Notice that I had to multiply both terms in this equation. What you don't want to do, even though it's technically correct, is to do that and try to integrate it. Vi is a constant, but it still is going to be end up multiplying by t. Whenever you do these kind of things, multiply each term by that differential there. So we're going to get rid of that so that we don't think that that's what we want to do. Okay. So now we're going to integrate both sides of the equation. So I'm going to get, let's do this up here. So I'm going to get vi dt is equal to the integral of plus at dt is equal to integral dx. Is vi a constant? Well, it's the initial velocity, right? And since it's the initial velocity, you can't go back in time and change it. It is what it is. So that is definitely a constant. And so I'm going to pull that out and I'm going to put it right here. Okay. How about a? Is a constant? Well, it doesn't have to be, but remember, we assumed that it was. And not only that, when we noticed that we plugged in this part, and I've written it over here, we plugged this part in right here into our expression, into our equation. Every assumption you make for this equation, therefore, applies to the next one. You can't help it, because otherwise this equation will be wrong and I couldn't keep going. So because I assumed I had a constant acceleration for this equation, I must also have a constant acceleration for this equation. I don't have the option. I have to make sure that that's constant. So I'm going to pull that out, and I get t dt, and then just integral dx over here. Okay. Make sure that all makes sense to you. All right, taking the integral of this is fairly straightforward. The first term here and the term on the right-hand side, I've just got the integral of the differential, which remember is just whatever I'm taking that differential of. So I get v t evaluated from ti to tf. Actually, I'm going to want to put this below the camera view here, so let's move it down just a little bit. So I've got v times t evaluated from ti to tf plus a. Now I need to actually do some work here. I need to remember some calculus. So remember, if I'm taking the integral of t dt, I raise the exponent. Right now the exponent's 1. I raise the exponent by 1, so it becomes a 2. So I'm going to have a t squared. But I need some coefficient in front, because when I take the derivative of this, I should get t dt. Instead, right now I'm going to get 2t dt. So I need a 1/2 in front of that to cancel out that 2 that's going to come around when I take the derivative. Okay. And then that is also evaluated from ti to tf. And then finally, the integral of the differential is just going to be x evaluated from xi to xf. All right, so I'm going to go ahead and do the subtraction here. Remember, we plug in here, we evaluate this minus whatever we get here. So we get v tf minus ti plus a. I'm going to pull the 1/2 out. Why not? Let's have a little room here. Because the 1/2 is constant. And that's going to give me tf squared minus, it's going to give me tf squared minus ti squared. Now, if you didn't like that, and you just wanted to evaluate this whole thing, you're just going to have a 1/2 tf squared minus 1/2 ti squared, and then you should be able to see you can pull it outside the parenthesis. All right, and then this parenthesis is just going to be xf minus xi. Okay. Now, before we start substituting around and solving things, which is number 3 in this microtask that you see on the page there, remember we made another assumption with this equation. What was the second assumption we made? We assumed that ti was 0, so that t becomes the elapsed time. I don't have a choice. I have to do that for this one. I cannot choose any other time than ti equals 0 because all my assumptions carry through. So this is 0 and this is 0. So when I do that, my tf then again becomes my elapsed time. So I get, this is, sorry, that should be vi. Let's go ahead and make sure we're keeping up with our subscripts here. That should be vi. Remember, that was my initial velocity here. vi t plus 1/2 a t squared is equal to xf minus xi. So now we're going to take this and we're going to solve it for xf. And you're going to write it in that blank right there on your page. I'm just going to do it here. I need to just move my xi to the other side and I'm good. So I have xf. Xi is negative here. I move it to the other side. It becomes positive. Xi plus vit plus 1/2 at squared. And that is my position versus time equation. Now, you may have seen some of these in high school, and you may not have known, well, why is there a 1/2 in front of that at squared? And your teacher was just, memorize it. The reason for it is because you took the integral. And that 1/2 comes about because of the integral. Now let's see if we can interpret what this means physically. This is, what are the units of position here? That's meters. So that's my final position in meters. Well, I'm going to go further if I didn't start at 0. So if I started my race 1 meter and then carried on, well, now I might get to 4 meters instead of 3 meters. So this then becomes my initial position, and it's the extra distance that I get because I didn't start at 0. So this is a distance, so it's also measured in meters. This is similar to what we did before. This is meters per second times seconds. So this is also a distance. And what this means physically is this is the extra distance I got just because I was moving at some constant velocity. Right? So I have this initial velocity. Maybe I started at 0, maybe I started at 1 meter. If I didn't have any initial velocity, well, I would just sit there, right? So I've got some initial velocity, and so after each second, I end up having a little bit further away from my starting point. But this still represents a distance. This quantity right here is a distance. It's VIT, and you would go, no, Dr. K, that's a velocity. No, when we multiply this whole term together, then this is also a distance with units of meters. Now, as you probably expect, this is also a distance. So a is in meters per second squared, and t is, of course, in seconds squared. Those cancel, and so the units for this one are also meters. So physically then, this is the extra distance I get because, so I've got my initial constant velocity distance, but my velocity is going faster and faster and faster. And so that's giving me some bonus distance as a result of this. So 1/2 at squared is in fact a distance. It's that extra distance I get because I'm accelerating from there. Now, the 1/2 again, there's no way to get that from the units because the 1/2 doesn't have any units. So if we were just using dimensional analysis, even if we were just looking at our units here, we wouldn't know that that 1/2 needed to be there. This is true for most equations. There's going to be some sort of constant. That constant is often 1. Technically, there's a constant in front of each of these, but it's 1. And there's 2 ways you can find that. You can find that through experimentation, or you can do what we did here and work it out theoretically, derive the equation, and then you see just from the integral that I did, I'm going to get that 1/2. So let's come down here and let's record our final position versus time equation. So that's going to be xi equals xf plus vi t plus 1/2 at squared. So let me erase what we've got here just so I've got some room to draw. Doesn't seem to be a way for me to highlight everything, unfortunately. I'm just going to clear out just a little bit of space. Now, when we've been working with position versus time graphs back in the first week of class, what was the characteristic curve for something undergoing an acceleration? What does that look like on your position versus time graph? So let's say I'm increasing this way, and this is my time in seconds, and this is my position in meters. If it was constant velocity, then it was just a straight line, right? What does it look like if it's accelerating? Think about it. It's going to look like this, right? Because the slope of my line, which is the velocity, is increasing with time. Well, this curve is a quadratic curve. That means it depends upon t squared. So if you took a bunch of data, right, and you had Excel or data graphing or somebody fit a curve to that, it's going to have the form of y equals at squared plus bt plus c. And now we can see, since y is my x, right? So that's x is a function of time. It equals a t squared plus bt plus c. So this term, b, must be my initial velocity. C must be what? Compare it to the equation that we wrote down here. Which one of these is C? Well, this must be my initial position. Here's something that's a little bit tricky that you need to be careful about. The A in this case is not exactly the acceleration, is it? If you look at your equation here, that A is the same thing as 1/2 times the acceleration. So this is actually half the acceleration. So if you actually wanted to pull the equation, the acceleration out of your graph here, you would say that A equals 1/2 my acceleration. And so that implies that my acceleration is actually twice that. So you just double whatever this number is, and that's my acceleration. But again, there's no way to get that without first deriving that 1/2 in front. Okay? All right. So now we've got the position versus time. We've got the velocity versus time. There's one more equation we want to come up with. We want to come up with an equation for the velocity versus position. Now for this one, we're not going to start with our definitions of acceleration or velocity because we already have an equation that gives us the velocity versus time. Go back and see if you can get that. So that's going to be velocity final plus velocity initial, or equals velocity initial plus my acceleration times time. And you hopefully made a flipbook page for that, right? Now, you should make a flipbook page for your next one as well for our position versus time. And if you want me to look at what your flipbook page looks like and kind of give you some feedback, I'm happy to do that. But remember, your flipbook page is going to have the name of the equation, which is the position versus time equation. It's going to have our assumptions, 2 assumptions, constant acceleration and ti equals 0. Then the equation itself, like you see here, and then we're going to list what each of these symbols are with its units. So xf is the final position in meters, xi is the initial position in meters, vi is the initial velocity in meters per second, a is the acceleration in meters per second squared, and then t is the elapsed time in seconds. All right. So what if I want an equation for the position versus the velocity, or velocity versus position? Well, I need to get rid of this time here, don't I? Well, I can do that very simply just using algebra. I don't need any calculus for this. I'm going to solve one of these equations for t, for time. I'll plug it in the other equation. And when I do that, then the time will go away, and I'll automatically have an equation that's for the velocity versus position. Now, it sounds easy, and it is, but there's a lot of algebra, and there's a lot of places that you can make mistakes. So we're going to go through this very slowly and make sure that we're getting this, and you need to make sure that you're working along very carefully with this one in your book. All right, so our first decision is we need to solve one of these for t, and this, by the way, should be at squared. There we go. We're going to solve one of these equations for t. Which one looks the easiest to solve for t? Well, the velocity versus time, right? To do the position versus time, I've got to use the quadratic formula and a whole bunch of other garbage. I'm going to get lots of square roots and all kinds of things. And engineers are lazy. So I'm always going to take the simplest equation that I can if I have to solve it. And that is definitely the velocity versus time equation. So let's write that down here and let's go ahead and solve it. So VF equals VI plus AT. I simply want to solve this for time. That's not difficult. So I get VF minus VI. I'm just moving that VI to the other side, equals AT. And then finally divide both sides by T. And I get VF minus VI over A, also a vector, equals T. So I've solved that first one for T. So I'm done with this. I can't use it anymore. You can only use these equations once. That's the rule. All right, so now I'm going to take that and I'm going to plug it into here. Right? I don't have a whole lot of space right here because my pen writes fairly large. So I'm going to take this expression and I'm going to plug it in for t right here and right here. And then we're going to see what we get. Okay, so let's do that. All right, so first off, I'm just going to copy it as is. So xf equals xi plus vf minus vi over a times t plus 1/2 a, again, I'm sorry, not times t, we already limited our t, didn't we? This is going to be times vi. Maybe I should put the vi on the other side just so you don't get confused. So this is t, this is vi, so we'll put that there so that we don't get confused. Okay, let's clean that up a little bit so you can read it maybe a little bit better. Vi, and then my parenthesis goes here. So this is t. Now I've got plus 1/2 a times t squared. So again, that's vf minus vi over a squared. Right? So that's how we've substituted into this other equation. All right, we're going to copy that down into the next box on the next page. Go ahead and scroll over to the next page. I'll do that in just a minute, but I'm going to lose my annotations if I do that. So work this along with me. So now I'm going to simplify this a little bit. Always simplify as you go along. Don't wait until you get to the end. You're going to give yourself just a load of heartache. All right, so we have xf equals xi. I can't simplify that. But now I can multiply through my vi. So I'm going to say plus 1 over a because I just don't want to have fractions and denominators and things. And I'll have vi, vf minus vi squared. Now I'm going to make one comment here. We've not yet talked about scalar products and vector products, which you probably heard of as being called a dot product and a cross product. If I have two vectors, there are two different ways I can multiply those. So give myself some room here. If I have vector A and I take the scalar product with vector B, then that's just going to be that times, you're going to see, times the cosine of the direction between them. Now, if I have the same vector though, then this just becomes a squared, and it's still a scalar. It's a scalar, it's not a vector anymore. So anytime I multiply two vectors together, they're going to become scalars. So I'm not going to get all in a twist if you say that those two are vectors, but technically they aren't, they're scalars. Now remember I said that if I have vectors over here, I have to have vectors in each term. Where's my vector? That vector is in the acceleration. So I do still have a single vector times some constants here. All right, then we're going to do this here. That's going to be, we'll say that that's 1/2, and again 1 over a. Now I'm going to square this, and so that's going to be vf squared minus 2 vi vf plus, running out of room, vi squared, and close. I'm not have room to close the parenthesis, but I'll do what I can. Okay. All right, so now I've already got some terms that I can simplify. Let's combine these two parentheses here. And again, this is on the next page in your book. I just don't want to have to recopy all this, and I'll lose my writing if I go to the next page. All right, so this is xi equals 1 over a, and then let's combine all these. So I have a vi vf minus vi squared plus 1/2 vf squared minus 1/2 times 2 is just 1 vi vf plus 1/2 vi squared. And again, I'm going to have to really squeeze my parenthesis in there. Okay, and that, by the way, should be a plus. All right, we can cancel out some terms. So you see that VIF and that VIF cancel. Now this is my notation. If something's actually 0, I will draw a line through it and then put a 0 up here. That tells me, okay, I shouldn't be looking at my algebra to see if I canceled something out. That really was 0, and so I just went ahead and substituted it. If I don't have something here, then I'll draw a line through it and just leave it like that to cancel it out. Some professors will even say, okay, these two go together if you're canceling out more than one. But since we are always going to do one line per operation, it's going to be obvious what we're canceling out. All right, so the next thing I can do then is I can combine these two VIs. I've got a minus VI squared and a plus 1/2 VI squared. Let's rewrite it because now we've got a little bit of room. So that's plus 1 over a again, still have my parenthesis. I'm going to combine this term and this term. So I'm left with a 1/2 VF squared. And now minus 1 VI squared plus 1/2 VI squared is going to be minus 1/2 VI squared. All right, now we want our velocity versus time equation. So I'm going to solve this for my final velocity here. So let's do it still one step at a time so we don't leave anybody behind. Don't make any mistakes. I'll pull my 1/2 out here. So that gives me 1 over 2a. VF squared minus VI squared. I want this by itself, so I'm going to go ahead and start moving stuff over to the other side. So that's XF minus XI equals 1 over 2a. These are vectors. VF squared minus VI squared, and these are not vectors. Okay. Now I need to multiply both sides times 2a, times vector 2a. And so I get 2a times xf minus xi is equal to vf squared minus vi squared. Now I'm finally done. And all I need to do is bring my vi squared, my minus vi squared over to the other side so it becomes positive. So I'm going to write this in down here at the bottom. So I get vf squared, that's what's here, is equal to positive vi squared, because I brought my negative to the other side, plus 2a xf minus xi. And this is my position versus time equation. Now you may say, Dr. K, why didn't you just go ahead and take the square root? And you absolutely can. It's fine. It is prettier if you leave it in the square form. From practical purposes, what actually happens is you work out vi squared plus 2a xf minus xi. You hit equals on your calculator, and then you just hit the square root button, and it gives you the answer. And as long as you remember to take that square root at the end, you're fine. But if you really wanted to take the square root of both sides, then you'd have VF equals square root of all of this. But you'll find that that's a lot harder to recognize and make sure that you're keeping straight. Okay. All right, and now then, if you had physics in high school, now you see why that's got a 2 in front of it. That came about because I have this 1/2 in both terms that came out. All right, so that is our position versus time equation, or position versus velocity versus position equation. Okay. So you should be following through on these pages, and then I'll go ahead and rewrite it on this last page so that we have it. So VF squared, which is not a vector for now, it goes VI squared plus 2A. That should be an X, XF minus XI. And again, we're going to want to make a flipbook page. Hopefully you've got them for all three. This would be the velocity versus distance or position. Let's call it position equation. Same assumptions we have because we use both of those equations. So it assumes A is constant. It assumes a constant acceleration. We also assume Ti is 0. So that T now becomes the elapsed time. Now, I don't have a T in this equation, right? However, if I used this equation anywhere else that did have a T, well, then I probably should keep my same assumptions and use the elapsed time for that, just to make sure. Okay. All right, then my equation is going to be this. It's just a good idea to keep up with all the assumptions that went into the equation that you're listed here. All right, and then I'm going to define my symbols, of course. And then VF is the final velocity in meters per second. VI is the initial velocity in meters per second. A is the acceleration, which is constant, in meters per second squared. XF is the final position, in meters, and XI is the initial position in meters. Okay, so now we've looked at the three kinematics equations, we've derived them, and we know when we can use them. Specifically, it has to have a constant acceleration. That is the most important thing. You will often get situations where you don't have a constant acceleration. In fact, in the real world, that's probably the norm. And you may say, well, Dr. K, why am I wasting my time learning these equations that don't apply? Well, the thing is that they give you that first cut that you need. You can say, okay, I know, for example, there's friction in the problem. And I know that that friction may be changing with time, or because I'm moving over different surfaces, or anything like that. Well, that's going to cause an acceleration. It's often going to cause an acceleration in the opposite direction from the velocity. But if that is small compared to, say, gravity or the motors of your robot, then for the first attempt, you can ignore that. You can say, okay, it's much, much smaller than this. It's not going to show up in my measurements, so I don't need to deal with it. Well, given that, then I have a constant acceleration. Then later on, after you have a kind of a big picture of what the motion's going to do, then you come in and you start analyzing it on a finer and finer scale. This is the reason why you can't have an AI or a numerical method, computer or whatever, solve your problems for you. Yeah, it'll do it, but often it will give extremely wrong answers. And you'll learn later in your classes what you have to do to actually get even semi-justifiable answers from numerical methods. And of course, right now AIs are just kind of confidently ridiculous. They'll tell you something that's completely, oh yes, this is the answer, and it's not even close. However, as my boss at NASA told me, saying, well, that's what the computer said, and having somebody die is not a good excuse. So your job as an engineer, even if you're using these numerical tools, is to look at what you know about the physics, simplify it down to something that you can at least get a big picture, and then see if this makes sense physically. If it does, okay, then we can trust the refinements that the computer is doing. If not, we go, something's wrong with that code. We need to go back and take a look at it before we trust it. Never trust a computer, and certainly don't trust it blindly. We'll see you next time.